Hi, good afternoon, and welcome to this session on Advanced Visual C++ and .NET Intro with Managed Extensions. Somebody probably thought my title was too long and cut out the most key word of the entire presentation. This session is how you take existing C++ components, existing C++ code, and move it forward to expose it to the .NET world, all of the .NET languages, or to take your existing applications and start using some of the rich .NET functionality we expose in the frameworks. I'm Ronald Laeremans. I'm a program manager in the Visual C++ team, and I work mostly on the compiler and on managed extensions and integrating C++ with the .NET framework. So we're quickly going to start off with an overview of managed extensions, which is just going to be a single slide, and then we'll immediately get into the meat of the presentation, which is how you take your existing codes forward and expose it to .NET. That will be discussed in three parts. The first part is showing how you can take an existing COM object and what the alternatives are for taking that COM object forward and exposing that as a first-class .NET object. The second part is discussing the case where you don't have a COM object, but you just have raw C++ classes, a raw C++ class library, and what you do there to expose that to other .NET languages. And the last part that we'll discuss is going to show a few examples, or it's going to show one example, actually, on how you can take your existing application. In this case, the example will be an MFC dialog application, and start using managed extension, through managed extension, start using .NET functionality from within my existing C++ application. So this is the first slide, and this is all I'm going to say about what managed extensions are. So to get a quick feel of how many people will be able to get along quickly, how many of you have already read about managed extensions and have at least gotten to the hello world stage of seeing like how it looks like and what it is? Okay, that's 1/5 or 1/10 of the people. So I'll try to spend some time on this. C++ as a language in .NET is placed on a very unique part. The other languages that Microsoft ships, the JavaScript compiler, the C# and the VB languages in .NET are all pure managed languages. All the code they generate is MSIL code. That's get JIT compiled at load time or at install time. All the data types they use are managed data types, value types or reference types. C++ is very different. C++ allows you to have a foot in both worlds at the same time. One foot in the world of unmanaged data types, in the world of x86 code that's generated from your compiler and your development machine, and one foot in the new world where you use managed data types that are fully described in metadata, and where you compile to MSIL, Microsoft Intermediate Language Code, that gets JIT compiled. C++ allows you to mix and match wherever those two facets are appropriate, both on a per file basis or even with lower granularity inside the file using some pragmas. One of the major distinctions is that we just added extensions to the language C++. We did not modify the language C++ to fit on .NET. We added extensions that allow you, that enable you to use .NET functionality from a C++ application. And one of the major things that means is if I throw the compiler switch that tells the compiler to compile my application as a .NET application, which is the CLR compiler switch, as you can see on the slides, then none of the semantics of my application change. If I write class foo, what the compiler is going to generate, it's going to generate MSIL code, which we specified by specifying the CLR switch, but it's still going to generate a native C++ class with native C++ semantics, which means we support a full C++ object model. Nothing changed. It isn't garbage collected. You still manage the memory manually. You still have deterministic finalization. You still have the support of the full C++ object model. Only if you modify a definition of a class with a keyword, and in this case either the underbar GC keyword or the underbar value keyword, am I going to create a managed data type. A data type just like you create by default in C# or VB that is accessible by all of the languages and that interoperates between all of the languages. This distinction between C++ on .NET and the other languages is a very important distinction because it will allow you to do some of the things we'll see in a couple of minutes in the examples. The main thing it allows you is to take your existing application, just throw a switch, so we generate them as IL, and from that moment on you can start using all the features in the .NET framework without having to change your existing code or translate into a different language or be recognizant that the semantics between .NET types and between C++ types are different. So this is a very powerful feature of managed extensions to C++. The 14 new keywords you see here were all added in an ANSI-compliant fashion, which means they all start with double underscores. The keywords in yellow I'm not actually going to describe. Those keywords map one-to-one to an existing .NET or a framework concept. They're basically exactly the same as they are in C# or in VB. Some of the more special keywords are the keywords in white. And the first I already mentioned, which is the GC keyword, which you use to attribute a class definition, saying that this class is not a class with C++ object model semantics, but it's a class with .NET with CLR object model semantics. It will be allocated on the GC heap. It will be garbage collected in a non-deterministic fashion, and it obeys all the semantics of the CLR object model. For instance, it supports multiple inheritance of interfaces and single implementation single inheritance of implementation. The other keyword to that effect is the value keyword, which you use to attribute a class or a struct to define a class that lives on the stack, but that is still described in metadata and it's still accessible by all the other .NET languages. You also use the GC and the no-GC keywords to attribute pointers to types to tell the compiler whether those pointers are GC pointers, so pointers the garbage collector has to track as pointing to live references, or are no-GC pointers, for instance, a pointer to just a native integer, which has nothing to do with the garbage collector and which requires no tracking information. One of the other illustrations of a keyword is the box keyword, which immediately brings me to explaining some of the fundamental philosophy differences between a language like C#, which also has a C inheritance or a C++ inheritance, and a language like managed extensions to C++. Managed extensions to C++ have tried very hard to keep true to all the aspects people use C++ for. And one of those aspects is being very explicit. The box keyword does a boxing operation, which you might know from C# and VB, is taking a value type, so a type that is allocated on the stack, for instance, like int32 or a point object, and being able to pass that where an object reference is expected. What is done internally by the CLR then is take the values, take the bits outside of the stack allocated type, create an object wrapper, move the bits, copy the bits over to there, and then pass this GC object. Since that operation is a fairly expensive operation at runtime, the C++ philosophy says you need to make this explicit in the language, which is why we added the box keyword. Whereas a language like C# tries to basically create a balance between being elegant and having to write fewer lines of code and still being able to give you the flexibility to do operations manually. So that's one of the illustrations where the two languages have a clearly different philosophy. There are several other places like this. Which means that in C++, you often have to write one or two additional lines of code, but the advantage of that is that you see where you're incurring a potential runtime overhead, so you can make sure you optimize that as good as you can. The other keywords that are in white here that I'll briefly go over is the identifier keyword, which allows you to create an identifier or use an identifier, for instance, a class name or a type name or a method name that conflicts with a C++ keyword or predefined identifier. Since the common language runtime is a common language runtime and it supports over 25 languages at the current date, it was impossible to restrict all identifiers to be a superset of all the keywords in all those languages, because there wouldn't be many useful names left over, seeing all the languages that have been ported to .NET. So we have an identifier keyword which you can use to specify to the compiler, I want to implement a class called bool or a class called for instance, and not have the compiler think this is a keyword in the language and give you syntax errors. One other keyword that is in here is the ping keyword, and the ping keyword is a crucial keyword for doing the interop. and we'll come back to that later. The pin keyword basically allows you to tell to the garbage collector that for some instance of time, which is the lifetime of the pinning pointer you declare, for some instance of time, you are not allowed to move this object, which is required functionality if you want to take something that is allocated on the garbage collected heap and then pass that to an unmanaged API, to a function written in unmanaged code, in unmanaged C++, because that function, of course, will not have the tracking info and would not be aware if that object moves that it has to update its pointers. So for that case, there is a pin keyword, so you can tell the compiler to emit some metadata that tells the garbage collector, do not move this object for the lifetime of this pinning pointer. I think that's all of the relevant keywords. There's also one new string literal prefix, which is the S prefix, which creates a white character literal that is stored in the metadata, which makes it a bit more efficient to create system string instances from than the normal white string literals. So the key benefits for managed extensions are that, seeing the design point, we have a very easy migration of existing code to the .NET framework. You just throw a switch, the /CLR switch, and the compiler will start generating MSIL instead of x86 code directly, and from that moment on, you will be able to start using .NET features from inside your application. When talking to some customers, like one way to explain this is, we basically have a very easy migration wizard. You just take your existing source files, you X-copy them over to a different directory, you throw a compiler switch, and from then on, you can start using .NET features in your application without needing to change any of your existing code or any of your existing logic. The contrary is also true. If you use managed extension to write an application that contains of mostly or virtually all managed code, but you still want easy access to what is there in unmanaged libraries, either the system, Windows 32 system APIs, or some library you have that is unmanaged C++, you don't need to add any declarations. You don't need to, like in C#, add DLL import attributes, because the compiler and the linker and the runtime work together, so you can transparently call both managed APIs and native APIs without having to do anything specific in your own code. The linker generates the necessary chunks that go from executing unmanaged code to executing managed code or back, and you don't have to manually do anything to make that work. So just including the header file, for instance, windows.h, is enough in your application to be able to call all the Windows APIs and linking with the import libraries. All the other languages, since they don't understand the C++ object model, basically have a narrower scope of their interop work. They can call, using DLL import attributes, flat C APIs, or they can call, using the TLB imp tool, COM APIs by generating a wrapper layer, and we'll come back to how that works in a minute. The other way around I already described, and there, for COM, there are tools to enable other languages to expose their managed APIs as unmanaged COM objects using TLBX and regjasm. And again, we'll come back later, seeing that you don't need those tools and have more flexibility using managed extensions. And as I said before, we allow you to create or to have both managed code and unmanaged code in the same application in cases where having parts of your code as unmanaged and part of your code as managed makes sense. One of the reasons, for instance, that some people prefer the slightly less readable optimized 86 code for some parts where they think they have IP concerns in their code and want to still compile that as native x86 code instead of as MSIL code. One other aspect is that if people have a part of their application they have tuned for a very long time in unmanaged code, they want to not have to redo that process, going to a new platform and a new compiler and be able to make sure the execution performance is the same as it always was for a core part of their application. So now we're going to get into the migration stages. And the first is you have an existing COM object and you want to expose the functionality, the API of that COM object to .NET languages, to CLR languages. So what you see here is I have my existing COM object which exposes a number of interfaces, and I have my native client that through COM through the interfaces and through functions like co-create instance and addref and release, creates an instance of that COM object and then starts making calls on that. There are two ways to expose that COM object to the .NET world. And if anybody of you has already gone to some other sessions on interop, you probably saw fairly detailed explanations on what a tool like TLBM does. That is one of the options. If you have a type library in your COM object, it's very easy to simply run a tool, and that tool will create a runtime callable wrapper, which exposes the API to all .NET languages, which you see here, which is the result you get after running TLBM on your COM object. You see the COM object on the right-hand side, still accessed through COM through my native client, and then see that TLBM created something called a runtime callable wrapper, or RCW, which allows you from all the .NET languages to call into this COM object. And then you see my managed client that through this intermediate object calls. This is actually a great solution since it's basically a zero-cost solution. You just run a tool on it, on your COM object, on your type library, and you get something without needing to expend any effort. Since everything that's free still has a cost associated with it, here are some of the costs in this case. Put in a different way, put in the way as to why would you want to use managed extensions to manually create that wrapping layer rather than having a tool do it for you for what is basically for free by just running it. One of the reasons is that certainly in server-side applications, and even more so if you're running it on SMP servers, that some of the data types that COM uses, that OLE automation uses, weren't really designed for scalability and for high performance on servers. For instance, beasters, the string type, or safe arrays, the array type or the aggregate type used in OLE automation, wasn't really designed to be a high performance scalable server solution. So one of the things beasters and safe arrays do is take global locks when creating and freeing instances, which isn't very good for scalability on the server. So since this TLBM tool can only read the type library and has to translate from what's in the type library from your existing COM interface to a .NET interface, it can't do anything more than just a literal one-to-one translation. So if you call to this RCW, if, for instance, your implementation of your ATL object had a normal character buffer, and at the COM interface you translate that to a beaster, and then you call through the RCW, what you will see is one conversion from your C++ or C data type to the beaster data type, and an additional conversion from the beaster to the system string, which is, of course, one conversion that could be avoided going in, and the same conversion that could be avoided coming back out if it's an out or a red val parameter as well. Using managed extensions, and we'll see that in a minute, you can basically bypass the COM layer and write a layer that does not go through your COM part of your ATL object or your other COM object, but that directly accesses the business logic, thereby avoiding this conversion and thereby completely avoiding the use of a data type like beaster. The second part, and if you're not constrained by performance, that's a much major issue, is that both the C++ object model and the CLR object model are significantly richer than the COM object model. Specifically, if you limit the COM object model to the OLE automation object model, which most people did to make it easier to integrate with VB6 and certainly with scripting clients that only understood OLE automation. So if you see that, a lot of people have a fairly rich C++ object model inside the implementation of their components that they then have to narrow down through a funnel, which is the COM interfaces, which is what COM allows you to expose. And then you communicate one-to-one on a low level through this TLBM created wrapper with those objects. Whereas ideally, you would want to expose an object model that's significantly richer to managed clients, since right now all the managed clients understand a very rich object model containing aggregate types, references, inheritance chains. So you want to expose a model that's probably significantly closer to what you already had in your implementation side rather than the flattened down COM object model. And the third part, of course, is somewhat similar, which is TLBIMP is a tool that just gives you one option. There's a few tweaks you can do, but in general, it follows a pattern, and it does all the translation exactly the same way. So if you want more flexibility to expose things in a slightly different way, writing your wrapper layer manually gives you much more control. So if you don't use TLB-imp, how do you go about exposing the logic in your COM object to managed clients, to .NET clients, managed extensions, J#, C#, VB, JScript? What you see here is our COM object on the right-hand side, called through COM by our native client, and we now see our lonely managed client that also wants to be able to use the functionality of this object. So what we do is write a very thin layer, which is a layer using managed extensions, so using some of the keywords I showed a minute ago, to talk to my business logic inside my COM component. Once I have written this layer, I now have an object that contains a mix of managed and unmanaged code. The interop layer is managed code. The other layer I can either compile as unmanaged code or as managed code, depending on what other constraints I have. And now that I have this layer, I can directly call in this managed layer from my managed client without going to this COM layer. So if you compare this picture to the picture we had before, which showed the TLB-imp wrapper, you immediately see that we don't have an intermediate step. So what I'm going to show here is an existing COM object, which is the product lookup component, which is an ATL written COM component. And I have several clients for this COM component. One of the clients I have for this COM component is the COM product client, which uses normal COM to access the functionality of this component. This is a command line exe that exposes a trivial part of the functionality. What I also have is a managed C++ or managed extensions client for this component that uses managed extensions, uses the CLR, and uses .NET to access the wrapping layer I'm generating. And what I also have is a C# client that's a WinForms application that also uses my managed API layer. If you look at my product lookup component, I already added the file, which is mproductinfo, which actually is my wrapping layer, and which follows a fairly simple pattern that I'll explain later in the talk when we're talking about wrapping C classes. It basically just forwards from a GC class or a JC interface to my existing native application in a fairly trivial wrapping fashion. So I have my COM product client set as my startup client. If I press F5, the product lookup client does something very trivial. It just gives you a list of products that are hard-coded, as an example, as a command line application. So what I'm seeing, if I can show you the source code, this is here I was in my COM product client, which is the console mode client we saw running, which basically just uses the pound import generated wrappers to call a COM object, and then uses the beasters, translates them to ASCII, and then just prints them on the console. So where I put my breakpoint is in the product lookup DLL, which is my COM component, which is the implementation for the get item description function of my interface, and where you see we just return one of a set of hard-coded strings. I'll remove this breakpoint and run it. Yeah. Press F5 a couple of times. So what you see, we get a number of products returned. So this was just showing that I had my existing COM client and my existing COM application, and they used COM to talk to one another. So what I what I add in this product lookup is add a GC class, which means that this class is not a normal native C++ class, but is a class the same as a C# or a VB class that is generating full metadata and that can be used by all the other languages. And I implemented these functions, as I said, as simple forwarding functions. They just call my existing business logic inside my ATL component without going through the COM layer, so without having the double conversions. So I just added these two files, this header file, and then the trivial implementation of these functions, which is here, which, as you can see, they're basically just forwarding functions that don't do much more than call their unmanaged side. So once I added that, and those files I compiled with the CLR compiler switch, the other files I can either compile with that switch or keep as native code, and the interop will be done automatically by the compiler and the linker. Once I do that, I can directly call this from managed code. And if I now switch to my managed extensions product client, and I look at the source file for this one, you will see that this is also a simple console line client, and that it has a pound using statement for product lookup.dll. The pound using statement in managed extensions is basically the equivalent of the pound import statement from reading a type library, or the pound include statement for reading the header file of a C++ or a C component, in that it reads the metadata in that DLL, which contains the GC classes I just added in this wrapper layer, and then uses that to populate the symbol table of the compiler so I can start using these functions. What you see in main is I'm using console write line functions, which is the CLR equivalent of printf. And then I'm creating this GC class here that I'm getting from my product lookup component and from the wrapping layer within that. And what I'm then doing is use a system string data type, setting it to empty first, and getting the item description, which I'm getting as a system string, and then again using console write line to step through all the returned items. So if I run this one, and set a breakpoint someplace, okay, this isn't useful, and step into here. What you see that now now I step from my client into my managed wrapping layer. The wrapping layer that gets my, that is the boundary, that operates on the boundary between the managed code and the unmanaged code. And if I step in once more, I see that I end up in the business logic of my original COM component. And we get exactly the same output. So to show you that, of course, C# can play in this world as well, I'll finally show you this C# client. Run that one, which should show as a message Windows Forms application. So there's a Windows Form application. And if I press the View Products button here, what you see in this C# code, I'm creating a new instance of my wrapping object. So breakpoint here. And then step into this one. So this is C# code that calls my managed wrapping layer. This is again my wrapping layer that I'm seeing. And when I step in here, I likewise end up in my existing COM component without having to use TLBimp and directly accessing it. Get rid of this breakpoint. And when this finishes, you basically see the same list in this box here in my C# application. So once I wrote this layer, I can, from all the managed languages, access my functionality. And what I didn't really show here, since the intent was to do a quick demo that you can show fairly rapidly, if this was a more complex interface, I could almost certainly improve on how rich the interface was going from COM to going to managed extensions. For instance, having inheritance or having links from one object to another object, or using something significantly richer than the COM iterator support we had. So going back to the slides for a minute. And wrapping up what we saw here, what we see on the left-hand side is the product lookup DLL, which contains the ATL COM support code, and which in this ideal case contained in a fairly isolated fashion my business logic. So isolated from the COM part, which makes it a bit easier to generate a managed wrapping layer. And then on top, we see a managed wrapping layer that's written in managed code, whereas the other two parts, in this instance, we still compile as unmanaged code. And you saw the existing COM product client that was an unmatched C++ client using COM that accessed through the COM logic, and in that case, the client used the compiler support for the pound import keyword. And then you saw both the managed extensions and the C# client application that called through this managed layer, and all calls ended up in this business logic layer. So basically, you see the same transition cost for the COM clients, which is through the COM layer to my business logic layer, as for the managed clients, which is through the managed wrapper layer to my business layer, which I think illustrates that you don't have the double overhead you have using a tool like TLBIMP and the RCWs that are generated. So the next part is, what do I do if I don't have a COM object, but I have just C++ classes or just have a C++ library? And as you already saw before, basically that scenario also applies in the case where you have a COM object, since writing your wrapping layer in general does not work through the COM layer, but will work by directly accessing in that wrapper layer your C++ objects. So what we're seeing here now also applies to the previous case, and that it is what you do in the implementation, even if you have a COM object where you want to expose a different and a richer API. So this is just an illustration of having an existing unmanaged class library and wanting to use that from the managed world. I again have my managed client that wants to use some functionality I already have in an unmanaged class library. So what I want to do is choose some points where it makes sense to expose parts of my unmanaged functionality to my managed clients. It isn't always necessary to expose all of my unmanaged hierarchy to my managed client. For instance, in most typical C++ class libraries, there's a lot of utility classes and a lot of utility support to make all the rest work that are only valid for the implementation parts. So in general, in almost all cases, you never want to expose the entire interface, the entire class hierarchy to the managed side, but only the top level objects, or maybe one layer beneath, where it makes sense to use those directly from the client side. Of course, you never want to expose something like a custom string type that the C++ library happened to use, because you want to use system strings and managed data types to do your processing on the managed side. So what we have here is I want my managed client to use this functionality. And how do I do that? I do that by moving over some specific parts that make sense to the managed world to my managed class library and plug them into my hierarchy in the place where it makes sense there. So the demo we have for that is going to show wrapping the CURL class, which is an ATL class. So apart from doing this to your own code, doing to the libraries you wrote yourself in C++, you can also do this to libraries, for instance, in ATL or MFC, where they have useful functionality to use in the managed world. And the URL class inside ATL is basically a class that allows you to split up a URL in all its constituent parts, which can actually be significantly more complex than it would seem to be at first sight. So what we have here is a URL parser project, which is a C# project, again, a Windows form, that calls the wrapped class I created in my CURL wrapper. And in this case, the system part is nothing more than a class provided by ATL. So what we see here is, this is the wrapping layer again for this class. I create a namespace because most APIs are exposed through a namespace, so you don't have these clashes at the global level. So we create a namespace to put this component in. And then again, you see the GC keyword here to attribute this class, saying it is a GC class, it's allocated by the garbage collector, it's released by the garbage collector, and it's directly usable by VB, C#, Mass, extensions, JScript, and so forth. And I again have this class that does the wrapping, have a constructor, destructor, and I expose some features of the underlying class in the richest possible way. For instance, what you see here is that we use properties instead of explicit getter and setter functions where it makes sense. There are a lot of C++ APIs, and C++ does not have the concept of a property built in, where people still follow the same naming pattern. And so it makes much better sense to expose these as real properties in the .NET world, rather than just doing a slavish one-to-one translation from the existing functions to managed functions. So what you basically see here is that we wrote this managed wrapper class that is just going to expose the functionality of my CURL class. And as you see here, this URL is very property-based because we create properties for all the constituent parts, which you'll see in a minute. There's also some other functionality like canonicalize the URL, so you get to the canonical form and create the URL. So if we run this project, let's see where I have a breakpoint someplace. This is again the C# code I'm showing. Let's get you some more screen real estate. What you'll see here is the very minimal part of where we had to write any user code. This is all generated code. Is the URL cracking. What we're calling here is basically this MATL, which was the namespace we created, and MCURL, which was the managed C wrapper for this URL class. We're creating an instance of this. And then we're going to get the properties and show them in some of the edit controls in this form. So this is the example. And if my mouse wants to play. We say crack URL, which is going to create an instance of my wrapper class, which you can see here. This is the constructor for this class, which will actually end up calling the constructor for this ATL class. I'm going to step into that constructor. And then there's a breakpoint here. And then we'll be returning the APIs as properties, which you can see here. So we parse the scheme, which is HTTP, the host name, the port number, which is 80, which is just the default, and the path, which is just a /path since we didn't specify anything. Let's say we would have a secure site. And some more. And we crack this URL. We would get that the port is 443, which is the default port since we didn't specify anything for secure HTTP, and that now we get a path that contains the path. I can't show you the browse button since I didn't hook up my network connection here. So, going a bit deeper into what this wrapping layer means. How do I wrap an existing C++ class? Say this is an example of a C++ class. I have my class called cfoo with a constructor, a destructor, and some member functions. How do I wrap this? The basic way to wrap this is create an equivalent GC class, so a managed class, which has basically the same functions. I create a private member, which is a pointer to my unmanaged class. You have to create a pointer. You cannot embed this. You cannot embed this class just by value. You cannot embed an instance. The reason for that is that a C++ class has a this pointer, and if you call methods, if you call instance methods on this class, they always have as the first hidden argument that you don't specify in this member the this pointer. Of course, if this unmatched class was embedded inside this GC type, and the GC would move this instance of this matched object, my enclosed object, my instance of my unmatched data type, would move as well, which means that the value of the this pointer would change. But of course, my unmatched methods don't have the tracking info to be aware when this pointer changes, and the GC can't change a value of a random pointer in unmatched class. So the reason that you can only have pointers to unmatched data types inside a matched class is the fact that the garbage collector moves the enclosing class, and you have to make sure that none of your unmatched code breaks. The compiler will flag this as an error if you try to create an instance and you have any member functions that have a this pointer. So in general, you create this object as a private member variable, and then you wrap all the other functions. The constructor just creates a new instance of this object, and the finalizer in this matched class, which is written in destructor syntax in both C# and C++ with matched extensions, is the finalizer. So that means the destructor or the finalizer for MC foo will be called when the garbage collector knows there are no longer any reference to this class. And then the next time it does its collection cycle, it will put this class on the finalizer list and then asynchronously call this destructor. One of the things to be aware there is this basically introduces multi-threading in all interrupt scenarios. Since the finalizers run on a separate thread, you need to be aware that your class has to be safe for the destructors of my unmatched class being called on a different thread from the rest of my unmatched class. So that's a caveat, and that's something you need to check your code for. In general, people don't do huge amounts of work in their destructors, certainly not things that would interfere with the normal work, but this is an issue you need to be aware of. So what are some of the basics? One of the things, of course, is you cannot inherit between a matched and an unmatched class or a matched and unmatched interface. If you think about this some more, this becomes actually fairly obvious. The issue is that an unmatched class in C++, if you create an instance on the heap, will get allocated on the normal C++ heap, the normal system heap, with no tracking information generated. A matched class will be allocated on the GC heap with tracking information for that class to be generated. If you were to allow inheritance from an unmatched class to a matched class, you end up with a very strange situation where the semantics of one part required to be allocated in one place and the semantics of another place required to be allocated in another place, which does not make much practical sense. If you want to pass matched pointers to unmatched functions, then you need to use the keyword I touched on earlier. You need to use the ping keyword to make sure that the garbage collector will not move your object while your unmatched code is doing something with that object, because otherwise, of course, you will be dereferencing the old location, which might be a stale location, or which might actually have another object moved into it by the garbage collector with very uncertain function, with very uncertain results. So you need to pin this pointer, which tells the garbage collector, leave this instance here at this memory location. There are no restrictions of using unmatched pointers in matched classes, which you already saw, because that is the canonical wrapping scenario, creating a pointer to this unmatched class inside your matched wrapping class. If you want to have a matched pointer in an unmatched class, so a pointer to a matched object inside an unmatched C++ class, then that doesn't work just by putting the pointer in there either. And the result there, again, has to do with the garbage collector. The garbage collector is aware of the exact layout of all the matched objects and is aware of all the matched stack location. So it can do its tracing, starting from your globals and your statics in your image, plus all the locations on your stack, and then trace down all of the cycle to where all your live objects are, going through pointers or references from one object to another. But of course, what the garbage collector does not know is how your unmatched data types are laid out, how your unmatched heap is laid out, because that isn't described to the garbage collector. That's just knowledge that's stripped away by the compiler when compiling unmatched C++ classes. So if you just embedded a pointer to a matched data type inside of an unmatched class, the garbage collector would not have any knowledge that this was a reference to a matched class that was existing. So two things would happen. The first thing is that if that was the only reference to that object, the garbage collector would, on its next collection cycle, just say, okay, I have no reference to this object, so I'm going to like free the memory and reallocate the memory for other use, which would make your object be a dead object. The other thing is that when a garbage collector moves objects, the garbage collector does not use a handle mechanism. The garbage collector and managed class in all our languages in the CLR use direct pointers. So a reference to a managed class, a pointer to a managed class, is a direct pointer to where at this instance, this class instance lives. And if the garbage collector does its collection cycle and moves that object, it will directly update the locations of all the pointers to that object. There's no double indirection through a handle. Which means that apart from being the only reference, if the garbage collector had other reference to my managed class, apart from the one in my unmanaged class, had other reference but decided to move this object when it compacted the heap, it wouldn't free the object, but would change the location of the object, but it would be unable to update this pointer that I have in my unmanaged class, and that pointer would again point to a stale location that might contain an old version of this object, or that might contain a completely different random part of a random other object. So you need to use some specific functionality, and that functionality is a GC handle class, which is a class that is exposed by the runtime. And that GC handle class basically is an explicit way to tell the garbage collector at this location in memory, which if it's a member of an unmanaged class will be a location in the unmanaged heap or on the stack. At this location in memory, I have a reference to a managed class of this type, to an instance of a managed class of this type. To make it somewhat easier to use that, we have a GC root template, which you can find in the vcclr.h header. And that managed template allows you type-safe access to the GC root, to the GC handle object. So you can basically templatize an instance of this GC root for whatever unmanaged objects you want to include, and we'll come back to that later in a small demo. And then use that as though you were embedding just a pointer to whatever managed object you were using. So apart from at the declaration side using a GC root of this managed type, all the other source code looks exactly the same since we have this template that we provide for you. Some of the issues to be aware of when wrapping unmanaged C++ classes is that certainly in this version of the compiler, we do not have support for default arguments. So you basically need to, if you have default arguments, decide whether to not expose the functionality of default arguments, or basically use overloaded functions to have the same effect as defaulted arguments. So if you have a function foo that has one integer as the parameter that has no default, and has the second integer as a parameter that has a default in another integer that has a default 0, you basically create the two overloaded versions, one with one parameter, one with two parameters, and have one call the other. The reason we do not support default arguments in this version is that it leads to somewhat strange semantics, since the CLR rules say that compilers do not, there's a way to emit default arguments into metadata, but the CLR rules state that other languages are not supposed to have to understand those default arguments, which means, and for instance C# does not, if you create, and VB allows you to create default arguments, if you create a function in VB that has one argument that's not default and a second argument that is defaulted, the C# compiler will only see that as a function that requires you to pass two arguments. And if you have a one argument function, will not even consider calling that function, which, if you combine it with overloading rules, leads to people having different semantics when called by different languages. If I had this function, and I also had an overload that took one parameter that had a float, for instance, and I passed 14, if I wrote a client in C++, if we were to have default arguments, the C# client would call the function taking a float, whereas the C++ client would call the function that takes one int and the other int defaulted. So to avoid these issues where you have to test your application with different client languages, we do not support default arguments, and we force you to write the overloads, which works for all .NET languages. The second point is that some data types don't look the same in the matched world and the unmatched world. There are a lot of data types that are exactly the same. An integer is the same in two worlds. A float or a double is the same in two worlds. Other data types, like strings, are not the same in two worlds. They have one representation in the matched world and a different representation in the unmatched world. So if you want to translate between the two, and if you write a matched interface and it passes text data, it should use a system string. It should not try to pass a character buffer or something like that. If you need to do that translation, then all the functions in the system runtime interrupt services Marshall class come in very handy. That is a function that contains nothing but static members, and all of those static members are there to allow you to translate from matched types to unmatched types, or to do things like manipulating unmatched memory. As you see, for the isomeric data types, for the data types that look the same in both, you have a lighter weight mechanism to make sure you can pass them from the matched side to the unmatched side. The other side has no concerns, and that is by pinning to make sure that those don't get changed. So if you were to have an integer that you need to pass from matched to unmatched, you would pin it. If you had something like a system string object or like a character pointer, you would use some of the functionality in the Marshall class that translates from a string to a character buffer or vice versa. The other point is that, and that is similar to what I said when you're when you're exposing the entire class hierarchy, that almost never you want to expose all the classes of that hierarchy because there are a lot of utility and helper classes. Even when you're wrapping a single class, or when you're wrapping a single class as part of a class hierarchy, in general, you do not need to wrap all member methods. One of the very simple issues is you, of course, do not want to wrap the private methods, since the private methods are by nature never callable by any clients of your application. They're only callable by your implementation itself. So you never have to wrap any private members. The other thing that you need to be selective about are parameters that are pointers to unmatched structs or unmatched classes. Say, for instance, I want to write a layer that exposes a matched API on the NT security API and some of the NT access control list APIs. Does it make sense in that case to try and expose the functions that take NT ACL structures rather than wrapping those in a nice matched class as well that doesn't have all the issues of memory management that the unmatched classes are concerned with? Well, the answer there is it depends. In this specific case, for instance, I would say yes. It still makes a lot of sense to expose, even on the matched side, APIs that take the raw unmatched data structure. And why is that? The reason for that is that NT ACLs in their self-relative form are often stored as physical structures on disk or transmitted over the network. So in the matched side, if you want to read an ACL that's stored on disk or an ACL that you get over a TCP connection, you still need to be able to pass a memory buffer that contains this physical representation and then use that to create, for instance, an ACL object. If that isn't the case and the unmatched data types do not generally have an on-disk format or a physical format that you need to read, it normally does not make sense to expose these functions, and you much better to write wrapper objects for these other parts of your structure or class hierarchy and expose them as matched objects with a richer interface. The other thing that is not directly supported is functions taking a variable number of arguments. There's no direct support, and that's something that's going to change in future versions, but in this version there's no direct support for having a variable argument member function of a matched type. So there you need to, again specify a number of overloads for these variable argument functions. And for the general case where you're passing a lot of arguments, have one of these overloaded functions, for instance, take an array of objects or take an array of typed objects if it's a variable argument function with a single type. And then the overloading rules will pick the correct one. So this is an example of how pinning looks like. What I have here is a GC struct. For the people that have mainly been reading C# code, don't be confused by struct here. Unlike C#, where struct means a stack allocated type and GC means a heap allocated type, a GC allocated type, in matched extensions to C++, the difference between class and struct is the same as the difference between class and struct has always been in C++. Class has visibility private by default and inheritance private by default. Struct has visibility public by default and inheritance public by default. and you use the GC or value keyword to tell the compiler whether this is a value type or a reference type. So what I have here is the same as GC class struct public :int I. What I have in the next line is a function that takes a GC pointer to the struct. So that pointer has the tracking info. The garbage collector is able to track that info and change the value of this pointer when it moves the object. But what I then want to do is call some unmanaged API function, which should be in the part where the comments are, to call some unmanaged API function that I can't recompile as managed code, where I can't change the pointer from an int pointer to a int GC pointer. So what I then need to do is create a pinning pointer, which is PPG. The first P stands for pinning, not for pointer to pointer. I create this pinning pointer, and then I can use this pinning pointer to pass to an unmanaged API, and I will be sure that the garbage collector does not move this object as long as my pinning pointer is alive. And so at the end of the scope of this function, the pinning pointer gets moved away, the stack gets cleaned up, the pinning pointer does not exist, and from that moment on, the garbage collector is again free to move this object. If I want more fine-grained control, I can explicitly set the pinning pointer to 0, to null, and from that moment on, the garbage collector knows it's free to move this object again. The only thing to be aware of here is that my function that I'm calling with this pinning pointer should not hold on to this object past the return from its function. If the first thing this function does, it's like store this pointer, put it in the database, and 3 weeks later, when you call the function again, retrieve it from the database and dereference the pointer, it's not going to work very well. That location will since long been gone. When talking to people about this the first time, and when we were designing this, we were saying, wow, this is quite a heavy restriction. This makes it very unsafe to use this feature. Like, you need to know that the code that you're calling is not going to hold on to the location of the pointer it's passed to. But in actuality, if you think about it some more, that does not turn out to be the case. Because if I have a function that holds on to the location of a pointer, even in normal C++ without a garbage collector, that's a very dangerous function. Because if I pass a stack location, the address of a stack allocated object is going to blow up just as dramatically as though the garbage collector moved that object. So in general, all the cases where functions hold on to values of pointers that you passed into it, and one of the famous or infamous examples is strtalk in the CRT, which parses a buffer according to what delimiters you specify, which holds on, so you can call the function multiple times, and then it just keeps on parsing the string and inserting terminators where delimiters were. That function is explicitly documented as holding onto its pointer and is heavily caveated as do not call it with the stack location if that's going to go away, and make sure that you're doing the right thing. The very few Win32 APIs that do that, very common set is the ones that do asynchronous I/O, where you need to pass in a request buffer. They all say, like, make sure this location stays alive until you call this retrieval function, for instance. So in all cases, this isn't a big deal because the functions in C++ that do this are very rare and very well documented to do the same. So apart from the simple wrapping and getting around some of the restrictions where the object models don't match one-to-one, what other things you can do? One of the things to think about is adding value. The CLR object model is a very rich object model, and it also has some additional features that aren't in the normal C++ object model. The three features that are new are properties, which are syntactic sugaring on getter and setter functions, delegates, which are basically somewhat of a cross between function pointers and pointers to members in C++, and events, which allow you to decouple function calls. So you can use that where we used Windows messages before, for instance, to send a message from a control to its container. So there are a lot of cases where C++ used patterns to expose those kinds of features, this kind of functionality. And it makes a lot of sense to really think about the C++ class you're wrapping, or the C++ class library or hierarchy that you're wrapping. And whenever you see a pattern that looks like a delegate or that looks like an event, properties are very simple, that's immediately obvious, but the other two, where there's a pattern that seems to imply that you're trying to do that, don't literally translate the pattern by naming convention or what else, but make them first-class events or delegates. The other thing you need to be aware of that the CLR does not allow people to write their own assignment operators and copy constructors. There's basically a bifurcation there, like you either have a reference type for which the assignment or copy construction always means create an extra reference to the same object, so I end up with two references pointing to the same object. And you have a value type, which means copy the bits from this object to this object, so I end up with two different objects that have no relationship anymore. And that's the only determination you can make. Whereas in C++, where you, on unmanaged data types, by using a copy constructor and by using an assignment operator, you can redefine the behavior at will. And you can have reference types that act as though they have reference assignment, and you can reference types that act as though they have value assignment. That is not directly possible in the CLR. The closest equivalent is exposing, implementing the iClonable interface and the clone function on that. Implementing that function basically is a marker to the consumers of your class that says, although this is a GC type, it should have value assignment semantics. But exposing this function, implementing this interface function, does not mean the compiler in any language will do that automatically. It just allows for the users to call this clone function to end up with two deep copies of the object. There are some caveats that have to do with some of the less fortunate issues that get caused by mixing a very rich existing system like C and C++ with, for instance, the macro preprocessor, which is the first thing we're going to touch on, with a very new world which doesn't have any header files, which has metadata that are stored in the same image. So the macro preprocessor can cause you some headaches. And since we ran into them first, I want to save everybody some time because you will run into these. One of the infamous ones that you almost immediately hit is that if you include Windows.h, one of the things you're including is somewhere on the order of several thousand macros that translate things that don't have an A or a W at the end to other things that do have an A or a W at the end. MessageBox is one that does cause problems since there is a class called MessageBox inside Windows forms. So if I include Windows.h and I try to create a class MessageBox, I'm going to get a compiler that says the namespace Microsoft.Windows.Forms does not have a class called MessageBox A or MessageBox W, depending on where you define Unicode. That's true. The reason for that is that the macro preprocessor is a very powerful tool and an extremely blunt tool. It will look at a token and translate that token. Whether I explicitly prefix that as saying this is system : Windows : forms : something, the macro preprocessor completely disregards that and says, oh, I find this string here. I'll replace it with this string there. Which is, of course, is needed by the way a lot of macros work, but which really wreaks havoc. So the only workaround for this is diligent use of macro undeffing and using the somewhat useful feature of macro pop and macro push that we have in the compiler, so you don't have to go start cutting and pasting definitions from inside Windows. If this is a function with an A or a W at the end, it is fairly trivial after that problem hit you once to immediately see what the issue is and how to solve it in 30 seconds. Some of them are a bit more subtle, is that some functions that were legacy functions, for instance, Win 3.1, aren't directly implemented inside of kernel 32 or user 32, but are defined as some other function with a macro. For instance, the exit Windows function actually calls the exit Windows EX functions with some parameters default. I think exit Windows EX has 2 more parameters, and they're both defaulted to null by the exit Windows macro. So those are a few other ones. If you write MFC applications and you start adding managed features to those, and you do a debug build, you will get the issue that the compiler gives you warning saying you're creating a managed class here, a GC class. You should be aware that placement syntax for managed data types is not supported. And why is that? That is because in debug builds, MFC defines new as debug new, a macro, and debug new uses placement syntax to be able to annotate all your allocations with the source file, the line number, and the allocation number of this allocation. And of course, placement new syntax is not supported in managed extensions on managed types, because the garbage collector decides where to place those things. So you'll get an error about placement new not being supported. The simple thing there is just not to define new as debug new. One of the other somewhat more subtle aspects is that you can get clashes to middle-generated interfaces that type-dev a struct as itself and then bind to the wrong version. The good way around that is to make sure you have your pound using statements before your pound include statements for things like windows.h. This only appears if you have a middle-generated header file that contains a definition for an interface that's also exposed in the managed world, and you include the unmanaged version first. So, again, this is the Marshall class. Marshall class contains a number of methods for translating data types between one another, for copying blocks of unmanaged memory from one place to another, which is significantly more useful in C# and VB, where there isn't any direct in-language functionality to that, and that you might use or might not use in C++, where you have direct access to functions like memset and memcopy, where you can do the same directly. And that allows you to do some unmanaged memory locations, and there again, there's no real need to use those in using managed extensions. One of the other interesting issues is that since the CLR is 32-bit 64 clean, since we're working on a version to run on Windows 64, that a lot of the cases where you want to use a pointer, like the marshalling functions that take a managed object and that return you the unmanaged equivalent as a pointer, for instance, the one that converts a system string object to the characters, to the buffer of characters that's stored in that object. Those return not a pointer, but an int pointer type, which is a 32 64-bit neutral type. So you have to cast those again to a normal pointer type, because there's no direct implicit conversion. This is one of the single examples on how to use this, where you see both of them illustrated, which is from the URL wrapper code that was in the demo a couple minutes ago. What we see here is the function string to h global ANSI called on a system string. And what this function does is create a new h global, so a new global memory block, and marshal and copy the bytes over there. Since this is the ANSI version, it will also do a conversion from wide characters to narrow characters. And then the to pointer here translates my in pointer to a pointer that's relevant for my platform, in this case a 32-bit pointer. And I then call my MFC, I then call my unmanaged function, passing it a normal narrow character pointer. And then finally I free up this global memory buffer by using one of the helper functions on the Marshall class, which is free h global, which you could do exactly the same way by just calling global free on that value. So the last part is a very quick example on how to take your existing application that is in unmanaged C++ and start using some functionality from the .NET world. And what I came up with is an example where I have an MFC dialog box style application, and I want to use some feature from the .NET framework. Again, I'll try to get some more screen real estate. So what I decided to use here in my MFC application is a very simple example of a .NET class, which is a regular expression matcher, which is a regx class. So what did I need to do in my source file? I have my existing MFC application that I just created using the wizard. I actually created this earlier today with the dialog box application. What I added here is a statement for using mscorelib.dll, which contains all the metadata for some of the base parts of the CLR of .NET. Then using systemdll, which happens to contain my regular expression parser, and then using namespace statement, so I don't have to prefix my regex type declaration with system text regular expressions. I also compiled, and in this case I chose to recompile my entire project with a /CLR compiler switch. I could choose to just recompile this one file or add a new file and just create this new file and forward through a function. So what I have here is I type in my email text in one of the edit controls. And there's the on button click. This is verify that this is a real email address with a very simple expression that only checks whether there's at least one ampersand in my expression. And what I'm doing here is using a managed data type. I'm using the regex data type that I got from the namespace. I had a using namespace up before. Pass it a string that contains my regular expression. In this case, it contains a marker for user and host, so I could get the matched parts that I'm not using here. I'm creating a match type, which is also a part of the frameworks classes that asks me whether there's a match for this expression, and then I check the return value of the success property on this match and say, yes, this is either an email address or no, this is an invalid email address. I'll run this. So I'll type in my own email address for the people wanting to take notes. And ask to check this email address. And what you see here is we're doing a new operation for this regular expression data type. I'm stepping through this since I don't have source code for this, doing the match. And then if this is successful, saying, OK, this is an email address. OK, that's what it's going to do. So if I go back, it says, yes, this is an email address. Let's say I'm doing the only thing that my stupid expression is able to detect and remove my ampersand. OK, I pressed on OK instead of check email address, so we need to do that again. Type in something without an email address and say check. It will go to the same expression, do the match. If it's successful, no, this time it isn't successful. So it will say, no, this is an invalid email address. So what you can see here is that apart from having to include the equivalent of a header file or the equivalent of a library, depending on how you see it, there's basically no barriers in my application to using .NET features and using unmanaged features. It looks exactly the same. I can, in the same application, without needing to do anything, this was an existing MFC application. I didn't need to change anything. All my existing code can stay there. But if there's functionality you want to use from the framework, and for instance, we have a very good, extremely fast regular expression parser that's up to par with the best native C++ libraries for regular expression parsing. If I want to use that, I just start using it. And there's nothing in my source code that I need to specifically do for using matched versus unmatched data types. For instance, as you see here, because there's a constructor for system string that takes both narrow and wide strings, I didn't have to create any intermediate objects to even do that. So I think this is one of the illustrations where your existing C++ applications can immediately start using all the rich functionality we have in the .NET framework without you needing to change any of the other parts of your application. Just the case where it makes sense, just start using those features and start using, for instance, some of the XML stuff or start using some of the functionality we have to expose something as a web service. So I think we already got through that since I'm a bit out of time. We already had that as well. We had the demo. So what are some of the additional resources if you want to learn about managed extensions and about the interop? One of the things to take note is we have a session on C++ futures tomorrow. One of the last sessions of the conference where we have Stan Lippman speaking. That could be pretty interesting. The other thing is there aren't any quick starts shipping in the release, including in the RC CD you got for managed extensions. So all the quick starts are on the got.net site under the late breaking chapter. You see the URL here, and this is also in your CD or on the website. The other thing is a lot of people from the product team are extremely active on the beta news group, and we try to answer almost all questions within 2 or 3 days' time, and in general much faster. So if you have any questions, I really encourage you to visit that resource. And that's the end of my presentation. I'm running out of time, so I'll take questions outside.